So it's a pleasure to introduce the first speaker, Edoardo Artioli from Roma, and he's going to talk about curvilinear virtual elements for solid mechanics with applications. Please, Edoardo.
Thank you very much, Paola. Thank you for the nice introduction. I hope you can hear me and you can see my presentation. Okay, so once again, I'd like to thank the organizers for the kind invitation. The outline of my talk is this one here, so I will just start with some motivations, and then I will just review the curved virtual element technology for two-dimensional solid mechanics applications. And I will present a gallery of recent applications we're being involved into, owing to material nonlinearity, computational contact mechanics, and last, asymptotic homogenization for fiber-reinforced composite materials. And then I will just draw some conclusion. So, typically, standard virtual and finite elements are based on meshes with straight edges. And whenever we have a domain of interest with curved geometries, this introduces a geometrical rectification error that can become pretty nasty in the analysis, especially for higher order schemes. There are several approaches in literature that have been devised in order to ameliorate this problem, such as isoparametric finite elements and isogeometric finite elements, for instance. Now, the virtual element method, in this case, in two dimension, actually offers a, so to say, natural extension to such cases, since virtual element meshes are made of polygons, and since polygons can have curved edges, this basically fits the bill for such an extension. So in the following, we'll see how to start from a standard conforming virtual element method, and by augmenting its displacement virtual element space in a straightforward manner, can take into account basically any kind of curved geometry given a proper parametrization of that. And one of the good thing about this is that we still retain the good approximation properties and accuracy of a standard, say, straight edge virtual element scheme. Now, getting directly into play, here we have the sketch for our model problem, namely the equilibrium for a two-dimensional body omega, having a curved boundary, which is intended as the union of a finite number of parametric curves gammas, which are intended to be explicitly known. And we look for a formulation, for a primal formulation in terms of displacement through the principle of virtual works, admitting that the material can behave in a possibly nonlinear inelastic constitutive manner, which will be taken into account as in standard VAM by a suitable and proper constitutive algorithm for the state of date of the material law. Now, as in, or very similar to standard conforming virtual element with straight edges, the construction of the global virtual element space for admissible displacement starts locally, and it's here generalized to the possibility of a polygonal virtual element with one or more curved edges, being as the collection of vector valued function that have a Laplacian, which is in pk-2, and have a polynomial restriction over any straight edge and have a mapped polynomial of degree k on every curved edge. So actually, we have the same global property of our unknown functions being totally explicit on the element boundary and fully implicit in the interior, globally continuous over a given polygonal element. For such a local virtual element space, we have, I should say, the usual local degrees of freedom, namely the point-wise evaluation of the displacement at the polygon vertices and the edge degrees of freedom for k greater than 1. And for k greater than 1, we have also the interior degrees of freedom, namely the area average moments against pk minus 2. So basically pretty much similar to a standard conforming PAM method, for which we have that through boundary degrees of freedom, we come up with a global space by gluing through the boundary degrees of freedom at the local element level. Now, the previous one is actually referred to as the original virtual element space for curved virtual elements. And in this slide, we present a novel form, an innovative form of such a virtual element space that has been devised in this recent work with Lorenzo Beirao and Franco Dassi, that is intended to somehow augment the preceding virtual element space, in as much it's designed so to include rigid body motions for our two-dimensional material body. And this is the pretty, I should say, simple to do in the virtual element method context, since it only requires to modify the edge restriction of our local virtual element space by defining it as the direct sum of two local edgewise space. The first one are taking care of including actually a linearized rigid rotation for the element, and the second one, and this one only owing to a couple of degrees of freedom. So perhaps the first and the last vertex of the curved edge can fit the bill, plus another local edge space, which is intended as a sort of a bubble space over the edge, which is added in order to complete to the desired degree key of accuracy. The good point, the interesting point, is that this, we call it RBM, augmented space, just uses the same type and the same number of degrees of freedom as the original one. So from now on, basically, the remainder of the construction of the method is still just identical to a standard conforming straight edge virtual element method. So instead of going back to these things that are probably already well known, I would like to just jump into some examples to show the properties of the newly introduced curvilinear method. Here we have first numerical set of tests that were carried out by Franco Dassi on a unit circle domain, and these basically owe to a manufactured patch test for the unknown displacement field, which is a trigonometric function, and for a material law, which is nonlinear elastic in the strain. As we can see here, we have tested several mesh types for order k equal to 1, 2, and 3. And we may appreciate that we have optimal convergence rates for the displacements and for the strains. This is actually this initial test on convergence is actually on the original curvilinear event space. Still, with reference to this domain, we have also made a comparison on another manufactured test, which is intended just to test the accuracy on represented reached body motion types of unknown displacement fields. And here we have made a comparison between the original and the RBM consistent formulation for the 3 mesh types and for cable 1, 2, and 3. And it's quite striking that we have the superior accuracy of the RBM in this extent. Now, another interesting example with material nonlinearity on a curved domain is the classical thick viscoelastic cylinder with internal pressure. And basically, we have considered a couple of material sets for which the loading case, which is a suddenly applied internal pressure, uniform pressure, which is just left there with the material free to flow, give quite accurate results with respect to overkilling solutions computed with standard isoperimetric displacement-based finite elements for k equal 1, 2, and 3, and adopting quadrilateral mesh, both structured and unstructured ones. Now, we have also made some comparison on accuracy between the curvilinear proposed vertical element approach and the straight edge vertical element original one. And we can see here on the table down on the right that still we have that the newly introduced curvilinear approach confirms its superiority in terms of accuracy for the radial displacement at the inner and outer surfaces, respectively, for both types of meshes. Now, another very interesting work we've been related to is computational contact mechanics. We have devised this in collaboration with the research group in Hanover led by Professor Riggers, and have applied basically the curvilinear approach in the original space version. And we have been able to actually assess a number of interesting things, mainly that basically all the tools connected to computational contact mechanics can still be retained with such an approach. And here we can see a couple of examples. On the left, we have the Gaussian contact problem of an elastic hemisphere onto an elastic horizontal half space. And on the right, we have an indentation problem between a spherical indenter and a spherical substrate. So basically this, on the one hand, confirms the accuracy and the possibility of obtaining smooth results in terms of contact interface stress patterns. And on the other hand, as I said, confirms the ability of the proposed method to be included in a standard nonlinear existence solver. Now, the third application I'm going to present is related to computational homogenization of a certain family of composite materials, namely fibre-reinforced composite materials, which I have sketched here in a couple of snapshots. These are materials that are made of a surrounding matrix material into which, in this case, straight parallel circular fibers are embedded either in a doubly periodic lattice, the upper cases, or else in a totally random arrangement, the lower snapshots. Actually, the application of interest here refers to random composite materials, and for their mechanical constitutive characterization, one of the possible approaches is asymptotic homogenization. Here we are interested in the so-called anti-plane shear deformation problem for a random composite materials, and this basically amounts to solving a problem such as the one that is here represented in the slide, where we have basically a grad equation for the auxiliary cell function T, which basically represent the longitudinal equilibrium equation for the domain, for the cross-sectional domain. Now, given the randomness of the material under consideration, in application of asymptotic homogenization, we are required to solve this problem on a portion, on a geometric window of our composite materials, which is termed as the repeating unit cell, or RUCQ. And at the end of the day, solving for the cell function over a repeating unit cell is going to give us the average shear moduli for the material. And by averaging over a sufficiently large number of RUCs, we're able to get a discrete statistics for the effective constitutive properties of the composite, and have its equivalent characterization. Now, the idea, hence, is to initially determine the so-called optimal size for the RUC for its averaging process to be meaningful to the extent of homogenization. And this basically is represented in this slide with the general rule that basically the lower the size of the RUC, the higher the number of sampling is needed, and on the contrary, the higher the RUC, the higher the computational cost is involved. So this problem here, given its geometry, really suits the bill for our approach, since we have that the domain of interest is really containing several curved interior interfaces for which a virtual element approach is suitable. Now, here just a few words. Here, the construction of the local VH is really the same as the original one for 2D elasticity, only the problem is scalar. In order to make computation more efficient and to cut off the computational time of the many of the numerous simulations required for an averaging process, we have also devised a residual-based, a posteriori estimator, which comprises 4 indicators. The first 2 related to the check on the local equilibrium equation, and the third one related to the enforcement of the continuity of normal stress component at the interelement interface, and the last one, the same check on the continuity at the fiber matrix interfaces. We have devised the usual type of adaptive refinement remeshing algorithm, namely solve, mark, refine, and iterate. And this proved quite interesting in applications when compared to standard uniform mesh refinement, as it's resumed in this slide, where we have analyzed a random composite material with different RUC sizes, and we have basically fixed a threshold in terms of accuracy for the homogenized material moduli, and compared the efficiency of the 2 strategies, namely with uniform mesh refinement and with the above adaptive mesh refinement strategy. And you see that the difference is quite encouraging, especially for the higher RUC size, where the outperforming of the adaptive mesh refinement strategy is really evident, as it's reported here in the table down right. So basically, we have been able to assess that curvilinear VAM are naturally suited for solid mechanics applications with boundaries that are curved, and that a standard conforming virtual element is achievable with just the same effort, the same number type and number of degrees of freedom as a standard straight edge VAM, so that many parts of our codes can be still retained, and this basically is also encouraging to proceed in pursuing for augmented formulations with higher regularity and possible other features. Okay, thank you for your attention.